Okay, so today we will continue mainly to focus on the example of three-dimensional gravity. But so before entering into the details of the asymptotic symmetries, let me just quickly go back to what we already have seen yesterday, just to clarify maybe some issues. So this is just the Einstein-Hilbert action written in first order form in three dimensions. So it's a formula that we have already seen yesterday, but just to clarify some things that maybe I flashed a bit fast yesterday. So no need to copy, so it's a formula that you already have in your notes, so it's just that I need it here to fix the ideas. And that we can also write clearly in this form, so I can make explicit what is the dependence on the spin connection inside the action. And I'm already using in this rewriting the dualized form of a spin connection. Okay, and just maybe a remark that I didn't made yesterday. So that's the term that you see here is clearly just the volume form. So this is the analog of the term square root of g lambda that you have in the Einstein-Hilbert action if you have a cosmological constant. So here there is these two first terms contains the curvature, and this term is just the volume form. So the things that I wanted to comment today is the fact that here, what are the equations of motion? So I can take the variation of this action with respect to the two fields, the field bind and the spin connection. And once again, here I'm omitting form indices. So all these objects are forms, and the index A is an additional label. So essentially, this is a vector of three one-forms, one into the other. So if I take a variation with respect to EA, with the action written in this form, it's pretty manifest that the equations of motion that I get is just this one. Which is the one that I found, that I wrote yesterday. So this combination must be equal to 0, and this is the equation of motion that is telling me that the curvature is constant. And the other one is the torsion equation. And in the case of a torsion, you just integrate by parts the exterior derivative. You get the sign that you have to get when you integrate by parts. And here you profit from the fact that there is an antisymmetrization here. These objects anti-commute. So you do a little bit of gymnastic, and eventually you get this equation here. So the structure of the terms that you get is really manifest. Because here I have a term quadratic in omega. If I take a variation in omega, I get something which is in E and omega, and that is the result. The only thing that you have to check are the signs and the coefficients. Yes? Omega square, you mean? Yeah, yes, thank you. Yes. Yes. Thank you. And the fact that here was a 6 and here is a 2 is just because I have 3 of them. And since there is an antisymmetrization in the indices A, B, C, and an antisymmetrization that is hidden in the wedge product, each time I only gain a sign plus, so they all sum. And so it's 3 times. Thanks. Okay, so but why I redid this? Because I wish to make a comparison with what happens in 4 dimensions. So in 4 dimensions, instead, the action has a similar form. But here I cannot dualize, so I have to keep this term outside. So also in this case, here you have, if you put together this term with the three field binds there, you get the volume form in 4 dimensions, and you have this term here behind. Here there is a number, since this is not precisely a cosmological constant. Well, I didn't have time this morning to fix it. You can fix you as an exercise. But this is the structure, and RBC, well, RAB, as I have written yesterday, is this object here. Maybe one thing that I realized that maybe I haven't stressed yesterday is the fact that the spin connection is an antisymmetric object. It is antisymmetric in the indices A and B. You can work even for something more general, but if it corresponds to Levi-Civita, it is antisymmetric. So in this setup, it is antisymmetric. So why I've written again this equation of motion? Because I've written this action because it's to make a little comparison between what happens in one case and in the other. So now the form of equations of motion. So the precise form is not maybe so important, so I will take the freedom of being a bit schematic here, because there is just something that I want to make to discuss with you, and EC wedge. So the important thing is that here I still have yes, and let me write what is the definition of a torsion in this case. Which I can also write in this form. So I got exactly the same objects that I had here, because also in this case this object is just a torsion. But here the two of them come bare somehow. There are no other objects contracted with them, while here I have several objects contracted with them. What does it mean that there are several objects contracted with them? This means that the equation is not setting to zero these guys, but is setting to zero a projection of these guys. So in both cases, these two objects are equal to zero. Now, how can we understand if this complicated projection still is putting to zero the whole tensor? You can do the exercise directly. For instance, in this case, you can contract these objects with two field binds in order to reconstruct the volume form and massage the equation, and at the end you can prove that eventually this projection, that this equation is actually putting the torsion to zero. Well, in this case, you cannot do, so there is always something that remains there. But how can we understand this? The reason is that RAB, so this is something that allows me also to better clarify the notation. As it was implicit in this construction, here I need to integrate a 4-form. So the curvature and the torsion are 2-form with these two additional indices. Okay, and similarly, the torsion is a 2-form with an additional index. But this, what is implying this? Yeah, so let me, okay, so that was to clarify the stuff. This means that if I just look at the components of these two objects, their structure is something of this type. So this, as a tensors, these components have this structure. And here, what do we find? So we find what we expect for the Riemann tensor, plus some extra terms. But all the extra terms are trace terms. So this is a traceless diagram of this form. You can say, come on, if you take this product, you also have, for instance, a full antisymmetrization. And objects like these are not present because this object is not the most general tensor 2 by 2. So as you know very well, in the metric formulation of gravity, Riemann tensors satisfy a bunch of properties. Now, you don't see in this formulation all the symmetries you are used to, because now these indices are very different one respect to the other, so you cannot exchange. But for instance, this object is still satisfying the differential Bianchi identity. So if I act with a covariant derivative, it gives me something that is proportional to the other fields. So it's not the most general object. This means that the other projection with more antisymmetrization are simply not there in this particular case. But this one is there, as you expect, because it corresponds to the Riemann tensor of a metric formulation, plus some traces. And here you have an object with this form. But why I did this small exercise? Because now let's look instead at the questions that I got. Yes, because be careful that here there is the important information of these two blackboards is that this is d equal 3 and this is d equal 4. So in d equal 4, I cannot dualize. So that is the structure that is true in any space-time dimension. So if I wish here, I can also work in 10 dimensions, say, something that you may see in the course of supersymmetry. And in 10 dimensions, I just have to put extra field binds there. And by the way, I profit also from the fact that maybe even people that that already have seen in classes the first order formulation, that is maybe not the most typical way of writing the action. You often see the action written in this form. Say the Lagrangian is something that contains plus the cosmological constant term. The two forms are completely equivalent. So it's just that I contracted the epsilon tensor, I rewrite, well, the difference is that here you have to put where this object is the determinant of a field bind. I mean, I will never use this one. It's just to say if you didn't realize what you are used to, it's just you can move from one to another. It's just a rewriting of the volume form. So it's the usual thing that the volume form, you can write something like okay, and similarly, you can move from one formulation to another. This is just a parenthesis. I'm not going to use this just to say that it is what you are used to. I'm not doing something crazier. It's just that to move to the 3 dimension is more convenient to use this formulation in terms of a wedge product of this object there. And going back here, the remark that I wanted to make is that the structure of this object, well, let's start from this one. So this one, the equations of motion that I get clearly have the same structure of the objects with respect to that I'm varying with respect to. So this means that the structure of this equation of motion is something of this type. Why? Because omega AB is actually an omega AB mu dx mu. Okay, so you see that this is the torsion tensor, and this is the structure of equation of motion that I get. So of course you have to do the exercise. I'm not gonna do it, but you can anticipate that at least the structure is the same. So if I act on this equation, I massage it, is not, say, maybe crazy that I can eliminate this term here and obtain an equation which is just TD is equal to 0. In the other case, you see on the other end that you have no chances to do it, because this is the structure of the equation. So whatever I do, I will be able to put constraint on the traces here. And indeed, the constraint that I get from this equation is that all traces of the curvature are equal to 0, which is the analog of Ricci equal to 0 that I get from this equation. But I have no chances to set to 0 the traceless window component here. So you see that in this particular case, the equation of motion will be a particular projection. In particular, eventually the equation of motion will tell me that all traces, where by traces I mean also traces that involve these two indices, mu indices A, are equal to 0. And eventually it's just the fact that the equation of motion that I get are equivalent to reach equal to 0. Or reach equal to 0 or Riemann equal to Weil, because if reach is equal to 0, then the Riemann is equal to Weil. In this particular case here, instead, I don't have any problem, because you see that manifestly RA, well, apart from the fact that the equation puts to 0 at face value these two terms, so it is manifest in this case that the two are equal to 0. But why this is possible? Because this object here has the same structure as spin connection, that we already know. It was something that it was already manifest at this level there. But in this particular case, also the field band has the same structure. Well, it's not that it has the same structure, because this is a two form and this is one form, but still I have a possibility to set it to 0. And why I have a possibility to set it to 0? Because this representation here simply does not exist in 3D. It's once again the fact that the Weil is trivial that is coming back in this particular condition, okay? So that is just to appreciate the differences between the two formulations, and even the fact that I can dualize the spin connection and the torsion. Here it's just due to the fact that some of the representations that are present in 4-dimension and Eiger are simply not present. If you wish, in this particular case, the spin connection is an object of this type. And in 3 dimensions, this representation here can be dualized in this representation there. So it's the counterpart that, yesterday I've been imprecise. So the correct statement is that if the number of boxes in the first 2 columns exceed the space-time dimension, then the representation is 0. And I can always dualize something in something that has half of a dimension of space-time. No? So in this 3 dimension, everything that has two rows can be dualized in something that has a single row. And if I have more than 3 boxes, it's simply equal to 0.
So the torsion has both components, the 3 form and the 2 1 in general? Some identities also for the torsion?
No, there are some identities also for the torsion, because there are some Bianchi identities also here. Well, I think so, but I'm less sure. So I should check it. Yeah, there are some identities also for the torsion, but I'm unprepared on this. I prefer not to say some wrong statements, but yes, there are some constraints also there. No, as I said, you have to do the exercise. This is just to. It's not enough to conclude, but it gives you at least an indication of why the situation is very different. So you really see that this case on which we focus is very special in this sense, but from a viewpoint of the algebraic properties of the theory, is just that some representations are equal to 0. This is an impact which is very important. I don't have propagating degrees of freedom, but still the structure I'm playing with are the same that I have in 4 dimensions. So in this sense, it is an instructive example to learn something also about gravity, at least in particular setups. Okay, so any question? So if there are no questions, this yes, sorry. There was, I forgot because it was on the back, last remark related to the differences between these 2 cases. So another thing, yesterday I put together all the connections into a Young-Mills-like connection. And again, I'm omitting the form indices, but here you have to think that this object, if you wish, this is something like, is a me, something like this. Where now these are the generators, say, of a Poincare algebra or of a anti-de Sitter or de Sitter algebra. This is true in any dimension. One thing that I can do once I have, say, absorbed all indices inside the definition of my Yang-Mills-like connection, I can compute the curvature of this object with just the Yang-Mills curvature, and the Yang-Mills curvature is something that you can split in this way. And once again, in 3D, you can at the same time dualize either this guy or this guy. So both guys can be dualized in something that has a single index. And then you know that the Yang-Mills connection is invariant under this type of gauge transformations, where the gauge parameter is also Lie algebra valued. And that is the gauge parameter of Lorentz transformation, local Lorentz transformation eventually. And this is the strange gauge parameter of local translations. And now we are going to see, to touch by hand, what is going to happen in the two cases. So now, I used this Yang-Mills connection just because I'm a bit lazy, so it's just to tell you that there are this gauge transformation, not need to write them explicitly in 3D or 4D, because you can just derive everything for this formulation there, since this is not the main point that I want to stress. So here we discussed the question of motion. There was another peculiarity, since it is important, because we are going to use it in the following. It's better to maybe clarify it as well. And it is what happens if I take these gauge transformations of the action. Okay, if you wish, this formula here is writing for me automatically two types of gauge transformations generated by lambda AB and transformation generated by xia. Okay? So this is something that algebraically I can produce in this way, and then I can check if this action and this action are invariant under these transformations, yes or no. Okay, a priori is not how I should proceed. I have an action, I should classify all the symmetries of the action. No, that will be the best way to do. But for the sake of the discussion, I can have an external machinery that is producing a gauge transformation for me. I verify if it is respected or not. And I have two types of gauge transformations, local Lorentz and local translations. If I look at the invariance of the action under local Lorentz, both actions are invariant under local Lorentz, and I invite you to check. It's a good exercise to do once in your life. But what happens if we take the transformations under local translations? If I look at what happens here, I look just at the transformation of the action under local translations, and what I get is the following. And okay, so I'm not going to do the exercise at the blackboard, but it's something reasonable, because if you look at how the things transform, you will find that DEA well, or to be even more precise, like this with this nabla is the Lorentz covariant derivative that we introduced yesterday. So what this means is that here I have in the action a term like this, plus the rest. If I substitute the Lorentz covariant derivative, the gauge transformation of this guy, in the other term there is only an omega, it is manifest that at least I gain this term here. I just integrate by parts. So you have to know that you can integrate by parts the Lorentz connection, but again, it's just an exercise that you can do. If you write everything explicitly, starting from the exterior differential, that you know you can integrate by parts, you can check that eventually all terms rearrange in such a way that you can integrate by parts this stuff. But this combination that we found here, it is precisely a Bianchi identity. So this term is equal to 0. So eventually, the action is invariant under local translations. and you say, okay, well, not surprising, because it looks like that everything can be written in Yang-Mills form is good. But actually, no, it is pretty surprising, because if you go here instead, you encounter the same type of problems that we encountered when we're computing the equations of motion. So I gain again a structure of this type here, but I have a curvature, but there is one field-bind left inside the gauge variation. And the fact that I have this field-bind left is important, because if I integrate by parts, I get, once the covariant derivative up to sines and all this kind of stuff is eating the Riemann tensor, and it gives 0, because it is, again, the Bianchi identity is also in this dimension, but there is also the term in which when I integrate by parts, I eat this guy here. And then the result is that this variation is not 0. So this action is not invariant under local translations, and is not, say, a surprise, in the sense that it's true that I could collect all the gauge transformations, all the structure of the variables, all the structure of the curvature inside a Yang-Mills connection, but the action is not a Yang-Mills action. It's something different. And the action is such that I keep the local Lorentz, and if you wish, you can already anticipate it from the fact that here I haven't written everything in terms just of A. I had to split it. So it's just something which is manifestly Lorentz invariant, if you think about it, but it's not invariant under local translations, and somehow the local translations are broken. They are there in the linearized theory, but in the theory, in the full nonlinear theory, they are broken. Okay, so here you see the differences. They are not crucial for what I'm gonna do today about asymptotic symmetries, but I think are important to just understand the differences between the two, so the peculiarity of a three-dimensional case. Okay, so that was also the back of the stuff. So I can go back to the discussion about the details of the 3D theory. So then this one I will erase, because for today we will forget about the four-dimensional theory. And I'm gonna focus on the three-dimensional one. So after all this discussion, what we discovered was that if I do what I've done here, so if I put everything inside this connection there, I can rewrite the Einstein-Hilbert action in this form. And this is where we stopped yesterday. And this is just a trace over the algebra. And well, that is something that I already have written yesterday, but let me do it. So for simplicity today, I will set G equal to 1, at least for this discussion. Otherwise, I have some G's everywhere that are just are not helping the understanding, but they are just messing up the formulas. And as I stressed yesterday, so this is either the Poincaré or IDS or de Sitter algebra, depending on the sign of L square. And L square is equal to minus lambda, L minus 2 in this particular dimension. No, what the L? Yeah, why I put a minus sign? No, this guy is positive. It is positive. Yeah, sorry. I think yesterday I put the minus sign, but This means that I have some typos in the lecture notes. Okay, never mind. So the important thing is that you get all of them. But that's not all, no? Because I told you what is the algebra in which my Young-Mills connection take form, but I haven't specified for you what is the trace, what is the killing form that I'm using here. And you can say, well, come on, you are dealing with simple algebra, there is a unique one. No, that is not the case, because the possible algebra are ISO 1, 2, SO2, 2, and SO1, 3. But this one is semi-simple, so there is only one killing form, so I don't have to specify anything. But this is clearly not. The Poincaré algebra is not semi-simple, so I have to specify for you what is the killing. Well, first of all, I have to see if it exists, a non-degenerate invariant form, and then I have to specify which one. For what concerns this group, or this algebra, well, it is typically semi-simple, the orthogonal algebras, but there is only one exception, and it is this exception here. And in 3 dimension, it's not semi-simple anymore because I can split it in 2. So when I write this action, I have to specify for you what is the killing form that I'm using, and the killing form I'm using is the following. So the trace is such that and all the other ones are equal to 0. So thanks to the fact that there is these off-diagonal terms that are different from 0, this killing metric is non-degenerate. So this means that it's important to have something which is not degenerate, because otherwise, if it would be degenerate, I would miss the kinetic term for some of the fields that I have inside the action, because here I want to have the derivative acting on all fields, so the fact of having something which is non-degenerate, it's important. And here you really see the structure that I got here. So you see that there I have E wedge d omega, and E wedge d omega is really coming out from the fact that here I have this term which is different from 0. So the kinetic term is manifest. And for the other one, you have to do a little bit of gymnastic to verify that if I use this trace, I plug this trace inside this spin connection that is written like this. I get exactly what, so the result that I have written on the blackboard before. Okay, so this is true in general, independently on the space-time dimension, but yeah, maybe I can do it here. Since in ADS3, the fact that I can split the gauge algebra in this way well, I don't have space. I wanted to do it there, but sorry, let's do it here. This implies that I can rewrite the very same algebra in a different way, in the sense that I can introduce these 2 copies of the generators. Notation is not optimal because L here is the inverse, is the radius of ADS, while this L is the generator of the algebra. And with respect to the notation that I used here, L is just the dual of MAB, is the dual of Lorentz transformations, okay? And I can introduce this generator there, and then the algebra can be rewritten, the very same algebra that I've written above, in this form. where you manifestly see the splitting in two SL2 copies. Because this is the SL2R algebra that you know very well. Why it is SL2 and not SU2? Because you said this, you are used to this, to SU2. Because here what is important is that I'm working with an eta IB, which is Minkowskian. So if you put, if you contract, and there is a contraction of indices inside there, no? Because strictly speaking, I should write this one as epsilon ABC, eta CD, J plus or minus D. Okay, so if you work with a Euclidean signature here, it is just the SU2 algebra that you are used to. If you use a Lorentzian one, it becomes SL2R. They are both real forms of SL2C, but they are different real forms, which means that the signature of the killing metric is different in the two cases. And the fact that there is a splitting is just due to the fact that these two algebras commute. So it's similar to the splitting on Lorentz into SU2 that you have seen in the SUSY class. Here it's just that it's a different signature is equal to 0. So, and you can do the substitution, so you just invert this transformation, you plug inside this algebra, and you can check that indeed what I've done is correct. And this means that in this particular case, only in ADS3, then I can also split the Yang-Mills connection that I have on the left in this form. Now, I will use sometimes this notation with a twiddle, sometimes a plus or minus also here. So here I put the twiddle because it's a common notation in the literature, and also sometimes having a lot of plus or minuses becomes a mess. From time to time, I will go back to the plus or minus notation also for this stuff. So equivalently, I will also write this stuff in this form sometimes. Essentially, depending if I wish to emphasize that I'm working with a single copy or if I want to write equation for both of them at the same time. So that is really not crucial, but just to fix the notation. And if I do this, again, you just plug in, so there is no definition, nothing. So you just plug this definition here in all the formula that you have written above. And what you find is also that these two objects, you can verify that they take these particular linear combinations. This is often, if you are interested by this part of the lectures and you want to learn more, this is typically the starting point of the literature. People do this because they told you, I can dualize the spin connection. Since I can dualize the spin connection, I can take these linear combinations, and then I can write a Chern-Simons action based on this linear combination. I prefer to start from the generic discussion to stress that ADS3 is not the only case in which you can do this kind of reformulation. So you can have a Chern-Simons formulation for all values of the cosmological constant. In the following, it's true that I will mainly focus on ADS3 because it's simpler, and my goal is to show you what are the properties of asymptotic symmetries, but still you can repeat everything also in flat space or in de Sitter space, and the basics remain the same. But if you do this, then you gain yet another simplification in ADS3. Again, this blackboard applies only to ADS3, not to all the other cases. And eventually you can see that the Einstein-Hilbert action can be even rewritten as the difference of two Chern-Simons actions. And why? Because this splitting, besides inducing this rewriting of the algebra, is also inducing a rewriting of the spin connection. Sorry, I haven't put in my notes. Well, whatever. So that's, I think it should be something like this. Here there is a number that I haven't put This is the only part which is different from 0. So from this splitting into blocks, you see that you can rewrite everything as the difference of two Chern-Simons action. And just to fix the notation, I'm going to rewrite everything as the difference of two Chern-Simons actions. But this is so that I can remove it. And the Chern-Simons action that is entering this very specific final rewriting. So let me rewrite it like this, just to emphasize it. It's something that I will write in the form K over 4p. That takes the same form. Well, let's put it like this, with two informations that you need here to complete the identification. The first is that K, it will be just L divided by 4G. And then you see 4 by 4 is the 16, so that is not a surprise. And the other information is that here, eventually I rescaled things in such a way in this form. So essentially, in each Chern-Simons action, now I am considering an A, which is equal to A mu A J A dx mu, and an A twiddle, which is equal to A twiddle mu A J A dx mu. And now I remove the plus or minus because I'm treating the two Chern-Simons action independently, and each SL2R algebra is such that I'm using these particular conventions, and clearly this convention there. So I've written everything in terms of a single SL2R, but if you want to do things carefully, you really move from SO2-2, then you induce the splitting with this redefinition, and you do the computation, and there's a computation that is telling you that eventually everything can be rewritten in this equivalent form. And this is the form that I will use from now on, while I'll be use this equivalent form, because since I have a sum, well, actually the difference of two Chern-Simons action, for most of the manipulation that I'm gonna do, I will focus on only one of the two. And so I will do all the manipulation in for Chern-Simons actions, which anyway is a gauge theory. So we are learning how to deal with asymptotic symmetries and charges in a gauge theory, in a particular one, but it's a specific gauge theory that allow me to extract information also about gravity. And the other advantage is that we'll see, we will learn how to appreciate the subtleties that are induced by changing the boundary condition, because in this case, I will do first a computation which is well adapted to Chern-Simons theorem, and I will explain you that this is not gravity, so I will have to go to gravity by changing the boundary condition, but it will be clearer in the following. Okay, so yes. I think that here I have what I need. That's one we can keep it for a while. So now the goal will be to discuss conserved charge. Yes? Yes and no. Yes, it's true. To really have it well defined, it must be integer. This is true because otherwise the gauge transformation, so the linearized gauge for linearized gauge transformation is not a problem. For the full gauge transformation, you actually need a K to be well defined. But this is something that well, we kind of ignore here. So you go in a regime, this is important if the cosmological constant Yeah, it's something that we are going to ignore from the viewpoint of the classical theory, but it's not that I'm ignoring for the sake of the discussion. This is ignoring most of the literature. Also because it's something that it will become, it should be important for if you quantize the theory. There it's very important. For the classical theory, to large extent, there are other subtleties that I'm going to discuss, but it's a good remark. That's true. So I'm going to ignore this point here. But at the level of classical manipulations, everything that I did is legitimate because it's just a rewriting of the original action there. So there was another question. Yes, yes, but it will become something more difficult. So if the level of the two Chern-Simons are the same, you are describing the Einstein-Hilbert action. So the chain of connections that I did for you is just writing the Einstein-Hilbert action. You can ask different questions. So for instance, can I change the level or I change the sign even, or this kind of stuff? What you produce are something that whose equations of motion are again curvature equal to 0. Because it's just the difference of two Chern-Simons action. But formally, if you look at the form of the action, you get either gravity with torsion. Yeah, essentially you have models that if you look at the action at face value, they look like gravity coupled to torsion with a propagating torsion. Propagating, yes, always in a sense that it looks like a theory that in 4 dimensions would propagate the torsion. So, and there are people that studied also this kind of stuff. You can redo everything that I'm gonna do also in this particular context. But strictly speaking, if you wish to have the Einstein-Hilbert action, the level must be equal. And we will come back to that later because you will see that the level will be proportional to the central extension that we'll find in the asymptotic symmetries, and 2 different levels will mean 2 different central extensions, and there are this kind of stuff. You can also add some additional terms of this form and get topological massive gravity. So you can make a lot of things. Here is just the most basic setup. I just want to do things that formally applies to Einstein-Hilbert. So I want to compute charges in Chern-Simons that I can interpret as being charges in a gravitational theory. Then you can start to play and do also more complicated stuff. But formally, yes, of course, you can define a theory like this, and given the identification that I discussed, it can be interpreted as a sort of gravitational theory as well. Okay, so we have seen already a lot of magic. There is a last magic that is important for us, and is somehow for the sake of discussing asymptotic symmetry is even the most important one. Well, it's a very important one, and it's just the fact that now I rewrite my Chern-Simons action. So the same Chern-Simons action that I've written here, yes, sorry, this is a nay, not a lambda. The same Chern-Simons action that I've written there. Now I want to rewrite it by making explicitly a splitting between time and space. And it seems, are you crazy? So it's so nice, this action, everything is written in terms of differential forms. Why I want to do this? Because I will display you that this action secretly is already in Hamiltonian form. And this is a great advantage because it will allow me to discuss well, I won't enter into the details of the comparison, but this is a context in which you can use both covariant techniques and Hamiltonian ones at 0 price, because the action without doing anything is already in Hamiltonian form. And if you use Hamiltonian techniques, identification of charges, who is energy is obviously much clearer in in an Hamiltonian formulation, because the energy is just given by the Hamiltonian. So then the splitting that I'm doing, here I have to, okay, I haven't stressed it, but this action, as we discussed yesterday, is defined on a certain manifold, and I want to have a manifold that topologically looks like anti-de Sitter. And anti-de Sitter, what is, especially in 3 dimensions, is particularly nice because I can really draw it on the blackboard, and it has the topology of a cylinder. So essentially, I'm going to introduce a radial coordinate rho, an angular coordinate theta, with a period of 2 pi and a time coordinate t. And that is the topology of anti-de Sitter. Again, if I want to discuss black holes, it won't be a cylinder, there will be identification, something like that, but close to the boundary, I just assume that the topology is the same as anti-de Sitter. So it's a nice cylinder. And for those of you that are familiar with the Penrose diagram of anti-de Sitter in any dimension, it is always an infinite cylinder. It's just that in this case, it is a cylinder. So I can really draw it without throwing away any two-dimensional sphere or whatever around. But if I do this, then I can rewrite the action in this particular form, dt d rho d theta. Well, I keep the trace, of course, which is important. A rho, and that's, this dot is just a derivative with respect to time. And then, in order to put the action in this form, well, let me write it, and then I will comment more. Okay, so why this is the case? Essentially, because here I have a term which is A wedge dA. I'm in 3 dimensions. I have 3 coordinates, t, rho, and theta. Clearly, the 3 of them, this is a 3 form. I can always, each index here, so essentially in the kinetic term, A wedge dA is proportional up to the conventions that you take for the antisymmetrization is this object here. Okay, so then this means that t, either it is on the derivative or it is on the field, and there are no other option. If it is on the field, I get this term here, where f rho theta is really the Yang-Mills field strength, or it is a derivative that is acting, and then the derivative can act either on rho or on theta. Okay, there are no other options, but this is telling you something interesting. So first of all, look at this term. So this is just PQ dot. So it's just the kinetic term of an action in Hamiltonian form. While what is this term? AT doesn't have any dot acting on it, so it's not a dynamical variable. So it's showing that inside the set of 3 components of A, well, there are much more because I have the 3 components given by the form index plus the components in the Lie algebra space. No? But if I plug everything the Lie algebra inside, I have AT, A rho, A theta, and then you discover that AT is a Lagrange multiplier because it doesn't enter anywhere, and A rho and A theta are canonical variables. So you see that I haven't done anything. The only thing that I did is to be it was an integration by parts, and I integrate by parts in order to get the term in this form, and I paid the integration by parts by this boundary term. But I didn't do anything else, so the action is already in Hamiltonian form without doing anything, and it is an action in which there is a Lagrange multiplier and a constraint. Why? Because it is a gauge symmetry. So we know that there must be, in Hamiltonian form, it corresponds to an Hamiltonian action with constraints, and the constraints there, in particular, it's only one. So if it is only one, it doesn't come in pairs. It can only be a first-class constraint. This constraint will be the generator of gauge transformations. Okay, and what else? No, I think that that's a very important thing to say at this level. So, yeah.
How many times it happens the Lagrangian theory is secretly already in Hamiltonian form? Did you see elsewhere?
Dirac action. So it must be a first-order action. So secretly, the reason why it is because it's a first-order action. So Yang-Mills, it doesn't have any chance to be directly in this form because it's a second-order action. So I may have situations in which I have a derivative that are distributed around.
And the thing is, so, I mean, couldn't you have, you said that since there is only one constraint, it must be first class.
Yes.
Couldn't you have, I mean, second class?
No, it's a good thing. So you could check if there are secondary constraints, and there are not. So that's true. That is a good remark. So I just overemphasized, but it's true. So the important thing is that it's so nice because you don't have to do anything. Of course, you have to check, but all the constraints are really manifest just by this rewriting. So the only constraints is f rho theta equal to 0. It must be a first-class constraint because it comes alone, and everything just by rewriting everything is written on the blackboard, and that is all the Hamiltonian structure that is there. Of course, it's true that a priori this is a good remark. You should compute the Poisson bracket with the constraints between the constraints of the Hamiltonian and see there is something more. And maybe a last remark, what could seem strange here is that there is no Hamiltonian, because I have a kinetic term, a constraint, but there is no H. But why there is no H? Okay, it seems weird. Maybe you are not used to have seen something like this, but it's pretty common because all theory which are generally covariant, so invariant antidifferomorphism, have a H equal to 0. So that is just a characteristic of the theory here. Okay, so are you all familiar with Hamiltonian mechanics? I won't use so much of it, but well, at least the fact that I compute a Poisson bracket and this kind of stuff. So the advantage is that the Poisson bracket that I will have to introduce in a bit abstract way in covariant ways, here is just the Poisson bracket. Once you have an Hamiltonian formulation, you know how to compute the Poisson bracket without any problem. So let me put here on this blackboard all the important things. So A theta, A rho are canonical variables. While AT is a Lagrange multiplier. For this particular constraint. And well, sometimes say, okay, I shouldn't do it, but for this part of the lecture, I told you that this was on shell. Today, let me use this to say that it's true on the surface constraint, something like that. So it's just a disclaimer for today, change the meaning of this symbol, and from tomorrow you have to forget this meaning again. But for today, we change it like this. And yeah, the other important things is that you can, since you know what's the form of a kinetic term, okay, the only thing is a slightly strange kinetic term because I have both with a dot. This means that I can choose who is a momenta and who is a canonic Q. So I can choose who is P and who is Q. And but the important thing is that the fact that I have this kind of freedom of choosing who is P and who is Q is just reflected by the fact that the basic Poisson bracket that I can write is the following. And where gamma AB is the inverse of the Killing metric. And here I'm using the fact that I'm gonna write okay, so here I just denote collectively the generators by TA because what I'm gonna say in the next half an hour at least is something that applies to any Chern-Simons theory. Then in particular, I will focus on a very specific one, but these are generic techniques. And then this means that starting from this basic definition, I can compute what is, well, maybe this is not a nice, let's say something like this. I can compute the Poisson bracket on two phase space functionals, which is just, here I'm stressing that I'm integrating over a disk inside the cylinder. And in this disk, yeah, d rho d theta trace of and this is just a functional derivative of it. Yes? Yeah. Yes, exactly. Yes. And we are going to see it, we are going to check that it's really generating the gauge transformations that we have into the game. Yes. And I must stress also that if you get interest and you look at some papers, so this kind of approach in which you split t, theta, and rho, sometimes not the basic one used essentially back then, but I think it's much more transparent, even including some papers that I've written where we use the different coordinates in ADS, but things are much less transparent if you. So this is really, it seems a bit pedantic that I'm working with t, rho, and theta and don't profit from some things, but it's, I think it's the best one to understand what's going on. Yes? The small... you mean this capital A here? Yes, I just put a capital A just to stress that the generators are whatever. So it's, I mean, it's just that the small a was something that was associated to this structure here. And essentially, if you wish, in the case of gravity, what I've... Yeah, that's true. So you are right. So if you prefer in this particular case, okay. So that is just because I wanted to have something extremely general, but you are right. In our particular case, I could rewrite everything like this. So this was just to stress that what I was doing is something that applies even for generic theories. But yes, in practice is this one. So it's just that, for instance, you can change algebra, and there are some contexts in which this is interesting, but we are not going to look at them. But for instance, if the algebra is SLNR instead of SL2R, you are describing eigenspin theories. And so it's completely general, and you can do the same kind of business. But yes? So it was some noise. dA, wedge dA. This term here. This one. So what's the question? Sorry. No, it is in the action. Yeah. Sorry. Because it gives an important contribution. It's here. Because this object, but that is a good remark indeed. I should have written explicitly. It's not a Young-Mills connection, this one, but it's really a... it is really there. And the fact is that you see, since it's A, wedge A, similar to that one. So A, wedge A, it's something of a form A nu, A rho, which is something of a form a certain number, possibly, and then it is AT, A rho, and A theta. So it is precisely the term that you get here, because you have the Lagrange multiplier in front, and then you have this term here. And you have to take into account there are the traces, the commutators, and the fact that the wedge product, yes, that's what I've written here is indeed is very cheap, because the important thing is that you have a trace of this term here. So this means that here you have a trace of these, which means that there are some commutators that are induced by the fact that you have an anti-symmetrization. Okay, sorry, that I should have specified explicitly. So it is just really a rewriting of what I had before. Okay. Yeah, and then maybe a last remark. So that is very important. So I know how to compute Poisson brackets. A last remark that is maybe not crucial for the asymptotic symmetry, but we will use some, but it allows us to understand better the structure, is that what happens if I take a variation of this action? If I take a variation, I will get for sure a term which is proportional to the equation of motion, so this is just a variation of the action, which will be a bulk term, but when I reconstruct the equation of motion, I have to integrate by parts, and so I gain some boundary contribution. One boundary contribution is already there. I also getting an additional one, and eventually this term will be equal to the equations of motion minus k divided by 4 pi dm dt d theta Now, that is important for, it's the first time that we see boundary conditions. So now I want to have a well-defined variational principle. So this means that I cannot put to zero both delta AT and delta AT here. So this is a matter of boundary condition. I have to decide what are the boundary condition inside the action principle. So to begin with, then things will be refined in the following. I wish to have AT completely free at the boundary. A theta, sorry. What does it mean, free at the boundary? It means that for rho that goes to infinity, I want to have A theta, the boundary value of A theta completely free. And that is the first time that we see a boundary condition in this setup. That is not a boundary condition which is appropriate to gravity, but for the sake of discussing how to compute charges in asymptotic symmetry is the simplest one. So pedagogically is the best option possible. And if A theta is free at the boundary, then this means that at the boundary, delta AT must be equal to 0. So this means that the boundary value of AT is a function in my game that I fix once for all, and is a free, essentially, function that is fixed once for all. So AT is Lagrange multiplier. Its boundary value is a parameter into the theory, and that's yes. Okay, so now what I keep, that one I keep. I can erase this one. Okay, now another advantage of this very special setup is that here I don't have to struggle if I want to see what is the canonical generator of gauge transformations, because my action is manifestly in canonical in Hamiltonian form, and so the generator of gauge transformation is just this guy, where there are some factors that are maybe not so important. Here I integrate over a disk again, d rho d theta, and then the generator is just this object here. So you see that the generator of gauge transformations take this form, but do you think is enough what I have written here? What does it mean? So that I'm wanting to find something such that delta lambda of, say, a mu, but in general of every field, is given by the Poisson bracket. So this is the meaning of a generator of gauge transformations. A canonical generator of gauge transformation means that a gauge transformation are reproduced via the Poisson bracket of this stuff. So that's well, the form, and we know that the generator of gauge transformations are first-class constraints. Now, do you think that what I've written is enough, or maybe something is missing? Well, of course, if I'm asking the question, it's because something is missing, otherwise I wouldn't have done. But that is probably what you have seen, of course, with different factor, whatever, but it's probably what you have seen in classes about Hamiltonian mechanics, because this typically is a way to see that first-class constraints generate gauge transformations. And what I've done here is just to write something that sometimes is called a smeared first-class constraint. But why use smeared? So smeared means that I say contract the generator of gauge transformation with an external parameter. But why you need to smear a constraint? You need to smear something in order to compute functional derivatives. Because otherwise, if you just have this guy here, you have to throw away the derivatives acting on the fields when you compute the variational derivative. Where do you throw the derivative? No? So you have to integrate it by parts in order to do the functional derivative. But to integrate it by parts, you have to throw the derivative on something else. And this is why typically you introduce this mirroring parameters that eventually it will be interpreted as being the generator of gauge transformations. But, well, okay, maybe it was a bit unclear, the explanation, but it's just that in order to compute functional derivatives, you have to integrate by parts. Because I want to rewrite everything. If I want to take the covariant derivative, the functional derivative of something, I want to rewrite, say, in the case of a Lagrangian, its functional derivative is something you can write dl as being d phi delta L in d phi plus possibly variation with respect to the derivatives. And eventually you wish to rewrite everything as being delta phi or something else, and what you have inside is the way to get the variational derivative. So I have to integrate by parts. But now, as we have already seen when I discuss this boundary term that I have there, I'm working on a manifold with boundaries, so I'm not on a sphere. Each time that I integrate by parts, I have to pay a price, which is a boundary term. The boundary term may go to 0 because I've selected suitable boundary conditions, but it's there. I cannot throw it away. So the way to write the correct generator of gauge transformation in Hamiltonian form is to add here a boundary term. Why I need a boundary term? Because if I look at what is the functional derivative of G, what I get well, let me write it. Anyway, I define, no, cannot do it. So this is a computation that I invite you to check, because it's the way in which you really verify that what I've written, so that this guy is the generator of gauge transformation, is really correct. Okay, if I take the functional variation of dg, what I get exactly what I wish. So in the sense that the functional derivative, look at what is the form of a Poisson bracket. If I take this functional derivative, I compute the functional derivative of my generator of gauge transformation, and this means that I will have to throw away these two terms here. What I'm gonna get precisely the form of a gauge transformation here and there. And the functional derivative of a mu is just a delta with a proper delta, delta in rho and rho prime, delta in the indices, all the delta that you need, but it's a delta, it's a bunch of Kronecker symbols. So you see that these first two terms here are just reproducing what I want. But in order to get there, here I have an unwanted boundary term, that I have to throw away to make this operation well defined. And this boundary term I can cancel just by having a non-trivial Q. And what is Q? Q is what gonna become my surface charge. Is the generalization, the most general thing that I can have in this Hamiltonian context is the generalization of what we did for the Komar mass. How do you see this? Well, you see here I'm integrating over a circle at the boundary of a cylinder. So here I'm integrating on a codimension 2 surface that is in particular case is just a circle. So at least at the level of dimensions, this is really an object which is an integral of something which has some nice properties on a codimension 2 surface. So in this particular context, these are the charges. And now what the next step will be. So now here I have a very simple, very direct way of understanding what are the charges because everything comes from this Hamiltonian formulation. And on top of this, I will have the right to really compute boundary Poisson bracket of charges. So we will see directly that the charges generates stuff. But so this guy here are the charges. And it is clear how to generate them. So there was a question.
Can we take this tool into account by putting a ribbon out into Lagrange instead of putting it by hand?
Yes, so you can start from the Lagrangian and try to derive everything. I think so. Well, especially it's particularly true for the energy, but you should be able to do it by everything. But that is kind of the simplest way to introduce. So here you have a very neat and clear prescription to see how to compute the charges. And we can see that these charges are the right objects because they will canonically generate the asymptotic symmetries eventually. But yes, that's I'm a bit less familiar. For sure, you can definitely do with the Hamiltonian. The rest, I guess so, but I would have to check. Okay, so now next step is that here we know that we have to introduce a charge, but that is something that it will be extremely important even when we will go for more general setup. The way to fix is that here I just have a delta Q. That will be something that will always come back. So the charges, I know the variation of the charges, not the charge directly. So I will never, whatever formalism, complicated stuff I can try to set up, this will always give me a variation of the charge. And then I will have to see if I can integrate this variation, and this a priori is not guaranteed, in the sense that if I have a variation of a function is equal to something, it could be that there is nothing that gives this particular variation. So what I have in mind is just, yeah, I should have thought an example. So suppose that I have something of this type, that delta Q is equal to A dA, that is kind of clear because this is 1/2 variation of A square. This means that this object is integrable, but it's not guaranteed. So you can have some variations that are more complicated with respect to that one. So there is no guarantee that you can put the delta outside of a given function and you can integrate. So this is why often this variation is written like this, while this slash means that is a variation that you have to see if it is integrable or not. So you can integrate or not. But that will gonna go back later. Yes?
So, if you don't include this boundary term, you just compute the variation of A as the Poisson bracket of the naive G, you get the gauge transformation plus
an additional term, yes. And so the typical way is that this additional term, you throw it away to make it consistent. So yeah, I think there should be some ways of presenting also in different ways. That is the most direct one. Yes, it's only a boundary term.
Saying that the full gauge variation of A is a standard bulk gauge transformation plus a boundary variation.
Yes. Kind of. Here I'm taking an extremely conservative viewpoint, which is the advantage why this is clear, because you can be ultra conservative, and in the sense that for me a gauge variation is something that does not have any boundary term. For instance, in a sense, you see that if you have a non-trivial Q, the transformation with a non-trivial Q are not generated by a first-class constraints because there is an additional guy there, and then they are not proper gauge transformation. This is a way. I'll try to elaborate a little bit more upon this point. It's a crucial point. This is why I like this example, because there I can say something more. It's not just, say, coming out of the blue or a... so I think I have, well, you will judge, but I think I have some arguments to argue why something that is generated by Q is not a proper gauge transformation, which are a little bit the typical ipse dixit that you find in some other approaches in which it comes from out. It may not be completely fully satisfactory also here, but it's the context in which I can say, I can do my best to try to explain it. Okay, so now just to conclude this issue of charges, so in this particular context, so if A theta is free at the boundary, so I'm not going to repeat each time at the boundary, I'm not going to write, but when I say free means free at the boundary, then at the boundary, all gauge transformations this means that at this stage I have no constraints on lambda 2. So lambda could be whatever he likes at the boundary. So it's an arbitrary Lie algebra valued parameter. In this case, it's an arbitrary SL2R parameter. But this means that when lambda is free too, this means that in this particular case, integrating this expression that I found is relatively simple, because here I found that the variation of the charge, it's something that I can write in the form minus k over 2 pi integral of S1 d theta trace of lambda delta A theta, and here you have an object here that is just, it does not depend on the fields. There's an arbitrary gauge parameter. Here there is something which is linear. Something linear is obviously integrable, this expression. So in this particular case, so let me stress in this case, because for instance, later we will see example in which lambda could depend on the fields, and if lambda, which means the gauge transformation that preserve the boundary conditions do depend on the fields, this trick doesn't work anymore. So you can encounter cases in which you have non-integrability. But in this particular case, this issue of integrability, I leave it aside. I'm not discussing. In a case in which integrability is for granted, then in this particular case, I can easily integrate the charge. And then I see that the charge is just minus k over 2 pi. And that's it. But the important information that we got from this discussion is the first, not the second. So this is always true. Oops, sorry. The second one is not. It depends on the boundary conditions. And yeah, maybe a last remark, which is not maybe crucial for the following, but here I've written an index mu. But if we look at what I have done, I only reconstructed part of the gauge transformations, because here I'm acting with a generator on the canonical variables when I do something. So I only reconstructed delta lambda A theta and delta lambda A rho. So where is delta lambda A t? The reason is that the gauge transformation of a t component, you can see it if you go back at the form of the action there. there is no Hamiltonian. So this means that the equations of motion for AT and A theta are just a pure gauge transformation. So in the sense that the equations of motion are of the form A dot theta or A dot rho is just and this is normal of all theories in which somehow you don't have any Hamiltonian. So here, usually in the equations of motion, you have a Hamiltonian here, but the Hamiltonian is equal to 0, you just have a pure gauge transformation. So, which is apparently weird thing, but it's not so weird. In this particular case, we don't even have gauge degrees of freedom, so the evolution is just a pure transformation. So I move from one time slice to another by making a gauge transformation that tells me what is the evolution. But on top of these dynamics here, I can always perform a gauge transformation here. I have a right. So this is telling me how I evolve from this slice to this slice. But then on this slice, I can do a gauge transformation of the fields. But if I do a gauge transformation, I have to modify accordingly the Lagrange multiplier in such a way that this equation of motion is preserved. So the delta lambda AT is just the gauge transformation that I have to do. After I did the gauge transformation, I have to rotate accordingly also the Lagrange multiplier in order to preserve this transformation, in order to make them compatible with time evolution. So that is a very complicated detour to get something that is very simple in equivariant terms, but like this you see that everything is consistent. It's just that the gauge transformation of a canonical variables are generated by this, and my Lagrange multiplier is just a guy that is there in order to guarantee this. It's completely inert, so it's not inert, so I can play with the canonical variables and don't forget about it, but it is important because it is there in order to verify that everything is consistent. Essentially. Okay. Well, it's super slow, but now, so that is the general setup, and I told you how to compute the surface charges, but at this stage, indeed, it's still ipse dixit. So I told you that these are the surface charges. Now I try to explain you why these are the surface charges, and to do this, there is a useful trick. This is a trick. It's not just a rewriting that is induced by the 3 dimensions. And I have a theory with a gauge symmetry. It's a trick that in 4-dimensional we'll do in a much more obscure way, but here I can do directly. So since I have a first-class constraints, I have gauge symmetry. One convenient way to analyze this constraint is to put on top of the first-class constraints and gauge fixing condition. So I want to fix completely the gauge. And after I fix completely the gauge, my first-class constraint plus the gauge fixing condition becomes a set of second-class constraints. Now, of course, you can object, but come on, you are trying to distinguish for us what are asymptotic symmetries, so the guys that become global symmetries, and proper gauge transformation. In which sense you do a gauge fixing? Well, in the sense that I propose you a gauge fixing, and then we are gonna check that is really a gauge fixing, so that is killing everything that should be interpreted as a proper gauge symmetry, and I will try to look at it from a couple of perspectives in such a way that we will get convinced that my gauge fixing is not gonna kill all transformations of this form, but is gonna kill a part of them, and this part of gauge transformation that I'm gonna kill are the one that we can interpret as being proper gauge symmetries. The one that remains are global symmetries or asymptotic symmetries. So I haven't discussed it yet, but what is an asymptotic symmetry or a global symmetry is really an analog of a global symmetry in a non-gauge theory. In a non-gauge theory, a global symmetry, for instance, so you have a free theory is invariant under rotations. And you say, this means that I can have an object that is spinning like this, but physics is invariant if I do a rotation. But this object or this object are clearly not the same. So I do something physical. So it's not a different parameterization of the same physical solution, because something that is spinning with respect to you in this direction is not the same as something that is spinning with respect to you in this direction. So physics, the equations of motion of this object are invariant under rotations, but these two solutions are not the same with respect to you. On the other hand, if in Maxwell I perform a gauge transformation, after the gauge transformation, the two values of the gauge potential gives me the same electric field and the same magnetic field. For you that you are in the lab and you are looking at the system, E and B are the same, so the transformation that I've done is just a redundancy of the description, it's a gauge transformation. So in the case of gauge theories, once you have a boundary, what is strange is that formally you have transformations that they all look like gauge transformations, but some of them will be associated to non-trivial charges, and the fact of being associated to non-trivial charges means that some of them becomes global symmetries, which distinguish one solution from a physically inequivalent one. And this is very weird, but how you can interpret, at first sight it looks weird, but how you can interpret this is that we said that here in, say, in gravity, we can define things only globally or asymptotically. What does it mean? That the only guy that is allowed to talk about the energy contained in an isolated source is someone that is living at infinity. Because if it is at infinity, essentially it's taking into account all the energy that is stored in the gravitational field. And an observer at infinity, it's something that you shouldn't do in gravity, but you can do because you are in infinity, is setting a preferred frame. So there is an observer which is preferred when we measure things, and is, for instance, you that is looking at a star far away, and you measure things with respect to something that is far away, because there is an observer that is observing the total energy. So a black hole that is spinning in this direction then is different from a black hole that is spinning in this direction for an observer at infinity. So of course I can change the reference frame. I can rotate you and reanalyze physics, but this guy will always change. So the fact that we have invariance under diffeomorphism doesn't mean that there are no observables, just that the observable are a bit tricky to encode. And what I'm doing is precisely that. So a rotation is a specific diffeomorphism, but come on, this black hole or these black holes are clearly inequivalent, because with respect to you, they are spinning in a different way. And what we are gonna learn is exactly this, how we distinguish the gauge transformation that encode these truly global symmetries that send physically some solution into another one, which is physically inequivalent. The weird thing is that I'm sending this black hole into this black hole, just performing what at face value looks like a gauge symmetry, but this gauge symmetry, it is not a gauge symmetry, because technically it is associated with a non-trivial charge, and in practice, because you are the observer that is deciding that the solution, so you are a preferred frame. It's a preferred frame that I don't have, I cannot use, and it's wrong to set up a preferred frame locally. Well, I can do to measure stuff, observer can do, but then I should be able to move from one to another with diffeomorphism. But once I'm asymptotical at infinity, I can have a sort of notion of preferred frame. Okay, so that's what I'm gonna do is try to give a technical counterpart for this stuff, but the idea is that asymptotic symmetries are just gauge symmetries. In the form, they are gauge symmetries that cease to be gauge symmetries because of boundary effects. And then, in particular, allowed to measure property. One of these charges will be just the energy or the angular momentum. The energy, I can change the energy, but the angular momentum is just this. Spinning in this direction or spinning in this direction is different, essentially. And we have to learn how to do it. And to do this, yeah, so now we have... So let's say that I put it like this, because I have to show you that I'm fixing the gauge. In practice, what I do is I'm imposing this condition. and where B is a group valued function. We'll see some example to fix the ideas. For instance, you can think one version that we will find in the following, it's something like this. For those of you that have already heard about it, it's similar to trying to analyze asymptotic symmetries in gravity in ADS in the Pfefferman-Graham gauge. So I just use part of the gauge symmetry to fix. It's an operation that sometimes is delicate, but in this case I will argue that the only thing that I'm doing is to fix the proper gauge symmetry. But I have a right to make these ansatz. The things that you can check, can I reach this gauge? Well, there are various ways to seeing it, but the simplest one, look, this guy is just a finite gauge transformation on A rho, but it's a finite gauge transformation of the connection A rho equal to 0. And well, here is, I have a theory in which the equations of motion are F equal to 0. So in a topologically trivial situation, I can always have one solution is just A mu equal to 0. So then it's clear that I can reach A mu equal to 0 and then perform a gauge transformation. What is really clear, important is the sentence in a topologically trivial situation. Of course, if I may have a topologically non-trivial structure in the bulk, that's I'm not able to do it anymore. But since I'm working, I want to define objects that are asymptotically ADS3 spaces. So close to the boundary, the topology of my space will be the one of a cylinder. So close to the boundary, I assume that there are no topological obstructions, so I can always do this. So this is just a gauge transformation of A rho. And we discussed quickly yesterday during the question and answer session, can I do things that are crazier? Yes, in some papers, you will find a gauge fixing which is A rho equal to 0. Of course, things becomes even easier, but the price to pay is that the metric will be degenerate in this particular case. At the end, the discussion will be the same. It's just that A rho equal to 0, I find it kind of a wild gauge fixing. I prefer to keep this, and in this sense, I have a G rho, which is different from 0. If I take A rho equal to 0, G rho will be equal to 0, so I prefer to avoid it, but for the sake of computing asymptotic symmetries, it's just a gauge fixing. You can even do things that are a bit more brutal. But here we keep this kind of stuff. So it's my choice. I can reach it with a gauge transformation. I hope I convinced you. And if I reach it by gauge transformation, now I just have to see what are the consequences of this. And the statement, just to anticipate where I want to go, is that if I add this condition on top of a first class constraint, these two constraints form a set of second class constraints. So all the gauge symmetry, the proper gauge symmetry is gone, but I haven't killed all gauge transformation. There will be some gauge transformations that remains, and this gauge transformation that remains will be my global symmetries. Now the task will be to convince you that what I'm saying now is correct. And yeah, so let's see. I try with the one that I think is the best shot to try to convince you, and then you tell me if you are convinced. And the idea is that on the constrained surface, if I impose this condition, the fact that f theta, which is d rho a theta plus a rho a theta equal to 0. So why I'm missing one term? Because I fixed a rho, and a rho has no dependence on theta because this is a function only on rho. So d theta a rho is equal to 0, so I only have this term. But if I have this equation, so this equation implies that the most general a theta takes the following form. And now I can look also at what are the allowed residual gauge transformation. So if there are gauge transformation of this form here that satisfy the that satisfy the conditions that I put. So here I'm not setting it, but somehow what I'm set. So I set a theta free AT as a boundary, a variation of the boundary which is fixed, and A rho takes this particular form. You can interpret it as a constraints that I put on my phase space in order to get to a second class constraint, but somehow I fixed the form of A rho asymptotically as well. So these are also my boundary conditions. So at the same time, I'm deciding how the fields goes at infinity. It's just in order to make things a bit more transparent, instead of fixing this form only asymptotically, I decided to fix it everywhere in such a way that things are a little bit more transparent. But sometimes you find also papers that tells you that A rho tend to this for rho that is going to infinity. And this is kind of what I'm implicitly doing because I told you that it's just close to the boundary because I don't want topological obstruction. So say that if I'm really on a cylinder, everything that I'm doing is true everywhere in space-time. If in more complicated situation, there may be subtleties. But on a cylinder, what I'm doing is true everywhere. And now I can look at the residual gauge transformations of this form. And preserving this condition that I imposed is not killing lambda. So there are still some lambda that preserve all the class of conditions that I imposed, but are simply lambda that takes this particular form. Sorry. And here I'm still doing it step by step in order to clarify who is what inside this stuff. So at the moment, I only imposed this equation and this one. So I just impose these constraints. So I'm not using all equations of motion because I'm not using all the ft something. And so for the moment, this guy still has a dependence on t. But if you impose on shell, this dependence of t is going away. But I'm doing it step by step to make it more clear from where this condition arrive. And the point is the following, that I told you that the Lagrange multiplier must be such that the evolution in time is preserved. So in particular, on each time slice, I must preserve the boundary conditions that I'm imposing. So, and in order to have this condition, this means that the gauge variation of, well, first of all, the Lagrange multiplier 2 takes this form, where again this guy only depends on B and this guy depends on A and T, on T and rho. But this, well, let me write because this is important. But this guy is the boundary value of the Lagrange multiplier, so it's something that is fixed once for all. It's what I told you, it's part of my way of setting the boundary condition. This I fixed is a parameter in my theory. Well, that you can interpret as I am fixed my frame at infinity in a sense. So if you go really to the details. So I decided that you are aligned like this and not just that you are 90 degrees turning in this direction. So I set my frame at infinity. But since this guy is fixed, then I can look at the gauge transformation of this object. And the gauge transformation of this object, I'm stripping already the B's, I already look at the small guys, and the gauge transformation of this object take this form here, but where the time dependence is completely fixed there. So this is a first order differential equation in T. What it's telling me is that the T dependence of lambda is fixed by this particular differential equation. But now if I have a proper gauge transformation, what does it mean, a proper gauge transformation? It means that my variables are defined up to an arbitrary function of time on each time slice along the time evolution. This is the right meaning of a gauge transformation. And here there is no any more time dependence. So in this sense, I declare that this is a complete gauge fixing because I completely killed the time dependence on gauge transformations. And it is something that sometimes people just impose all the equations of motion in one shot to say that there is no time dependence. But I think that like this should be relatively transparent, because I really set some boundary condition on each time slice. I let the system evolve, and I teach place on the evolution. So the only thing that I can do is to do a gauge transformation in which I decide what is the gauge transformation on a time slice. And this gauge transformation, I can only let it evolve on all time slices. So I don't have the freedom to perform an independent one on each time slice. But still, I have the right of performing a gauge transformation, which depends on t, on a given time slice, and see what is the effect. It's not the same, because there is a non-trivial dependence in t there a priori. It depends on the precise condition you put on AT. It could be that it's just the same rotation everywhere, but well, okay, I'm not sure it is precise, but in a sense it's just I decide on a time slice how to turn, and then I inherit this decision everywhere. It's just deciding that you are aligned like this and not aligned like this. So it's just choosing my frame at infinity in a sense. And this is why the remaining transformations are really global symmetries, are just that I can either rotate my frame or rotate equivalently my object. So it's really deciding what it is. Looks convincing? Yeah. Yeah, then maybe I can try to conclude. Even more slower than expected, but I hope that is useful anyway, the discussion. Maybe I conclude with yeah, because I just concluded with the alternative methods to try to see that these are second class, but that is maybe less convincing, but just to have another perspective, and then I conclude and we continue essentially tomorrow. And so the other possibility is that you just compute explicitly the Poisson bracket within the two constraints that I put here. And here I just put a rho because this B is not a function of a canonical variable, so putting or not putting doesn't change anything. And then I want to argue that this is the Poisson bracket, which is adapted to a second class constraint and not a first class one. And notice that here I have a smearing function, but here I really want to have the commutator between the first class constraints and a rho. So this means that I choose a function that goes to 0 at the boundary. So I want to kill the Q, because to really focus only the first class constraints, and I can do it by using a smearing function which is 0 at the boundary. And if I do this computation, I know what is the result. And the result is that just d rho is a gauge transformation anyway, because here I don't have subtleties with the boundary terms, precisely because the boundary terms are killed. And this equation here is such that if I have a boundary condition that this smearing parameter is 0 at the boundary, the only solution of this stuff is that it is 0 everywhere. So essentially it's telling you that this Poisson bracket is non-degenerate, as it should the Poisson bracket of a second class constraint. So I know that you would prefer to see something different from 0 here on the right-hand side, but that is another argument. But I think the previous one about the time dependency should be the one more convincing, to say that I killed all proper gauge symmetry because I don't have the freedom to do arbitrary transformation of time inside. And okay, after this long detour, I eventually fix all the stuff, and then I can go to the computation of symptotic symmetry just to conclude next time, and then we go to 4D. Okay, thank you. Yeah, you can do whatever you want. So I think you have in mind these edge mode constructions. Yes, so you can put a theory on the boundary and try to involve, but that is kind of more advanced setup. This is maybe helpful also to fix the problem with K, because if you have a theory at the boundary, it's taking care of the gauge transformation there. Yeah, you can do many things, but that is kind of more advanced topic. As I said, so this is just an example, although it's taking a lot of time, but because I can do everything very, I mean, in detail, I hope. And, but yes, you can also do more advanced stuff. I think it's what is called edge modes. So you can try to compare, to interpret these asymptotic symmetries as the existence of boundary degrees of freedom. You call them edge modes, but I'm not gonna discuss this. So that's for sure.
Okay, very good. So a few minutes break, and at 11.